series Lcr circuit. So this circuit explains that when the resistor, inductor and a capacitor, all the three are connected in series, means if the alternating EMF is equal to E sin naught omega t will be connected to that. How far these things will be happen in the same circuit? Already we know that when the pure resistor, when the alternating EMF is connected to resistor alone, both the current and the voltage will be in the same phase, both are in same direction. But for inductor, we can take that current will leads that will be the voltage and current direction will be pi by 2. Then for the capacitor, that is IC. Here we are substituting the Ohm's law, V is equal to IR, V is equal to IR, V is equal to IR. Here for the resistor, resistance value is R. For inductor, the resistance value is inductive reactance. For capacitor, the resistance value is capacitive reactance. So this is a graph shows. Okay, that is a current, this is a voltage direction. Let us see that. So applied EMF is equal to E naught sin omega t. So the current flows in a series circuit. For the amplitude of the resistor, voltage resistor, there will be a voltage curve. So the amplitude must be V naught into I naught, or I naught is the amplitude of the current, V naught is the amplitude of the voltage when the EMF is alternating EMF is flows through the resistor. Again I will say that I naught is the amplitude of the current when the alternating EMF E is flows through the resistor. Then V naught is the amplitude of the voltage curve, that is when the current flows through the resistor. This is V naught. Similarly, we can write the amplitude of the voltage in inductor, amplitude of the voltage in capacitor, by simply using the V is equal to IR formula. We are taken only the amplitude value. Amplitude value represents the peak value of the particular graph. So this is a phasor diagram for the series Lcr circuit. So this is a voltage. Inductive voltage is greater than the capacitive voltage. We are taken that inductor voltage is greater than the capacitor voltage. So what we will get? So this is a current value. The current and the applied voltage will be in the same direction. Current and applied voltage will be in the same direction for resistors. For capacitors, the current value and the voltage value is 90 degree behind. So you may ask the question, sir, in capacitor you draw that the current value is in this direction, but for the series circuit, for the capacitor, for capacitors the current phasor diagram is in the positive y-axis, but for in the series circuit you are drawn in the negative y-axis. Don't confuse with that. Here we are taken that the voltage is in this direction. This will be a says that, as I told, that the voltage lags behind the current by 90 degree. So that will be explained here. Okay, this is the voltage. So the 90 degree, from the 90 degree it will be lags behind. So that is represented here. This is a VL. VL means that is the inductor voltage will be applied in this direction. So are you able to identify black color? This is a voltage resistor curve. This is a capacitor curve. This is a inductor phasor diagram curve. So these two are opposite signs. So the resultant vector will be, this is a bigger value, this is a smaller value. That's why we are taken as a VL is greater than VC. When VL is greater than VC, so this will be a bigger amplitude, this is a smaller amplitude. The resultant vector will be along this direction. That will be a VL minus VC. So we have to take the parallelogram law vector for VL minus VC and VR. So if you take the VL minus VC as a one vector and VR as another vector, so the resultant vector will be in this direction. So resultant vector will be in this direction by using the parallelogram law of vector. The angle made by them is a pi. So the angle made by them is a pi. So in phasor diagram, for the voltage inductor voltage is greater than the capacitor voltage, we have to draw the phasor diagram in this manner. So again I will explain to you one more time. So this is a voltage of the resistor, this is the voltage of the capacitor, this is the voltage of the inductor when they are connected separately with the alternating EMF. If they are connected in the series with the same circuit, we have to draw the phasor diagram in the same diagram. So then we have to take the resultant vector of VL and VC. So VL is greater than VC, so it will be along the VL direction. So this is a one vector, VL minus VC is a one vector, VR is another vector. So by using a parallelogram law of vector, so the resultant vector will be EMF will be goes in this direction by making an angle pi with the VR. So this curve is called as a impedance triangle. That is, the inductor reactance is greater than the capacitive reactance. Inductor resistance is greater than the capacitive resistance. We will see later. So as VL is greater than VC or in the opposite direction, their resultant is VL minus VC, as I am explained in the diagram itself. So by parallelogram law of vectors, the resultant vector of VR and VL minus VC must be equal to the applied EMF. That's why I am saying that the resultant vector of the, by using the parallelogram law of vector, VL minus VC and VR, the resultant will be the applied EMF direction. So by using the Pythagorean theorem, so E naught squared, which is equal to VR naught squared plus VL squared plus VC squared. I will say that. So by using the Pythagoras theorem, the hypotenuse square, which is equal to this one and this VR square. So by using the Pythagoras theorem, we get that. These are all in amplitudes. For amplitude only I will put V naught. In diagram I will show that it is in the voltage. Just you put the in suffix V naught, we get the amplitude of the corresponding voltages of resistance, inductor and capacitor. So E naught, so V naught R is a I naught R. That is I naught XL for the inductor, I naught XC for the capacitor. Then taken I naught commonly outside, we get R squared plus XL minus XC the whole square. Here also I naught squared will come. Okay. So what is E naught value? That is I naught value. You have to bring this paragraph, this bracket to the denominator in this side and taking the square root. We get I naught is equal to E naught by root of R square plus XL minus XC the whole square. So clearly this root of R square plus XL minus XC is a resistance of the whole all L and C and R. That means inductor, capacitor and resistor connected in series means the amplitude of the total circuit current is I naught. The amplitude of the EMF is E naught. Then this denominator will be represents that the resistance of the circuit. So that is a effective resistance of the series LCR circuit which opposes the flow of current through the circuit. So this is called as a impedance. So again I will say that when we connect the alternating EMF with the resistor alone, the resistance is R. For inductor alone, the resistance is inductive reactance. For capacitor alone, it is a capacitive reactance. If all the three are connected in series, we get the total current value. The total current value amplitude is I naught. Then the applied EMF amplitude is E naught. So I is equal to V by R formula by using the Ohm's law. This denominator terms must be equal to effective resistance of the circuit. We give the name for this total resistance of the circuit as a impedance. It is denoted by Z. So the SI unit as it is, this represents the resistance of the circuit. We give the SI unit as a ohm. So Z is equal to root of R square plus XL minus XC the whole square. By substituting the XL value and the XC value omega L minus 1 by omega C the whole square, we have to represent this one. Okay. So in this diagram represents when the VL is greater than VC. That means inductor voltage is greater than the capacitor voltage. Some of the circuits work on the basis of the inductance coil working. So that cases we have to use this condition. Then certain circuits components will work based on the capacitor. So for that we have to take an VC is greater than VL. That means VL is less than VC. For that case, very simple. VL is a smaller value, VC is a bigger value. So the resultant vector will be come in this direction. So as usual, what will happen? The EMF, here you note down that EMF is between the y-axis and VR axis. In between then only the applied EMF resultant vector will come. But for this case, you observe that this is a VR vector. So the resultant vector will come this direction. So pi. So there will be a certain changes. But what is the difference? VC is greater than VL. Here also we get the impedance triangle. Impedance triangle as a xc minus xl. Here the r, here the z. This is the pi value. If you draw this diagram, we get that. Similarly, the impedance triangle for the VL is greater than VC or the XL is greater than XC is same thing. So only the term changes is here XL minus XC. Here XC minus XL. So this is the impedance triangle. So now, very simple students, we have taken the resistance, capacitor and inductor connected in series. Already we studied all the three things, or if you are connected in separately with the alternating EMF, we arrive the phasor diagram. So we have to draw the combined phasor diagram like this. So that will be explained clearly to you. So by using this phasor diagram, we arrive the expression for total resistance of the circuit, and we denoted as a impedance as a letter Z. Now, what are all the special cases? When XL is greater than SC, that means VL is greater than VC, that circuit is called as a inductive circuit. So inductive circuit means that circuit will be worked based on the inducting property of the wire. So or the circuit. So EMF is ahead the current. EMF will be ahead the current with the phase angle pi. So EMF will be ahead the current with the phase angle pi. So tan pi which is equal to XL minus XC by R, or cos pi which is equal to R by Z. So cos pi will be calculated by using the impedance triangle. So cos is equal to adjacent side by hypotenuse. Here the adjacent is R and hypotenuse is Z. So we substitute that cos pi is equal to R by Z. Then tan pi which is equal to XL minus XC by R. So what is XL minus tan pi? Tan pi is the opposite side by hypotenuse. Here the opposite side is XL minus XC. For XL minus XC, for that XL is greater than XC. This diagram, XL minus XC and the hypotenuse is Z. So we arrive the equation tan pi is equal to this one and cos pi. Then the instantaneous current is equal to I is equal to I naught omega t minus pi. Then when XL is less than XC, this cases the same thing. So tan pi, instead of XL minus XC, we have to substitute XC minus XL. Then cos pi as it is, because the cos pi term never changes, both the adjacent and the hypotenuse. Then I is equal to I naught sin omega t plus pi. So this is a minus pi because EMF is against the current. Here the current is against the EMF. Dear students, I hope that you are understand that very simple, don't confuse. This is a very important question, repeated question. So we are writing the special cases for XL is that is inductive value is greater. Here the capacitor values get greater. Then now what will happen if the inductor and capacitor value are equal, means the pi will be 0. So EMF and the current will be in the same phase. So this is series Lcr circuit is called purely resistive. Then I naught is equal to E naught by Z, or E naught by Z, or I naught by root 2 which is equal to E naught by root 2 Z. So the amplitude of the current is equal to EMF amplitude by the resistance, impedance value. What is the Z? Z is equal to root of R square plus XL minus XC the whole square, everything will come. Okay, so here I will in the denominator I will substitute root 2 and both the left side and right side. So I naught root 2 and I naught root 2, E naught by root 2 into Z. So I naught by root 2 is IRMS, E naught by root 2 is ERMS by Z. So what is the susceptance? So listen here. So very simple, when XL is equal to XC, that is we are going to see in the next question, resonance condition. So in resonance condition, the impedance Z is equal to R. So in this case also impedance Z is equal to R. How the impedance Z is equal to R? If you substitute that Z is equal to R square plus XL minus XC the whole square. If XL and XC are equal, means both will be cancelled, become 0. So root of R square. So root of R square is R. So Z will become R. Hence we say that here the circuit is purely resistive. So there is a susceptance, means a reciprocal of the reactance of an AC circuit. This is a reciprocal of the reactance. Admittance means reciprocal of the impedance. Listen here, impedance and reactance are the same physical meaning, but there is a difference in that. So reactance means it is a resistance of the either the capacitor or the inductor. but the impedance means the resistance of all the three are connected in series. That is a resistor, inductor and capacitor, all the three are connected in series means we have to say that for the effective resistance as a impedance. So just we will give the different names for reciprocal of these two things. So next question we are going to see that the resonance condition for series circuit. I hope you are understand this Lcr circuit, that is inductor, capacitor and resistor connected in series. So understand the phasor diagram clearly. So don't confuse that. If you draw the phasor diagram clearly means very simple question. We arrive the equation for the impedance, and then we substitute the special cases. The inductor is greater and the capacitor is greater, and finally inductor and capacitor are equal.